Okay, in our lab this week, we'll be looking at two principles of fluid dynamics that we'll introduce here now. The first is known as the continuity condition. Let's consider what happens when water is flowing smoothly and there's a change in the cross-sectional area and the dimensions of the tube or the space that it's flowing through. Now, you've got to have the same amount of fluid passing this point each second that you do passing this point. Because if you didn't, that would mean that fluid was either appearing or disappearing in the middle, and that's just not possible. That's really what the continuity principle says, and that's typed out here for you already. So we've got to have the same amount of fluid at these 2 points. That amount of fluid is what we call the rate of flow, and let's see what that depends on mathematically. So rate of flow is the amount of fluid each second, so let's consider the fluid that's going to pass a point in a second. Now, if that fluid is moving at speed v, then the length L of this little element of fluid here will just equal the speed times the time t. Let's just turn on Do Not Disturb. Where is Do Not Disturb? It's there somewhere. Do Not Disturb is now on. Okay, sorry about that. All right, so now that's the length. This tube has cross-sectional area A, and an idea from basic math is that a volume is a base area times a height. So the base area is A, and the height is just this length L, which we've just shown is the speed times the time. Now I've got volume V and speed V, so I'm going to try and make them look different by writing vol here and using a script V for the speed. So the volume rate of flow, we said, was the amount of volume per unit time, and we see that that is going to depend on, after we divide by time and cancel out the t, the volume rate of flow is going to depend on the cross-sectional area and the speed of the flow. So what our continuity principle tells us is that at any 2 points, this volume rate of flow has to be the same. So we'll introduce a symbol, rate of volume flow. Now that's going to have units of cubic meters per second or liters per second because we defined it as a ratio of volume over time. So that's definition. The principle tells us it's got to be the same at any 2 points, 1 and 2, or initial and final. So we saw that volume rate of flow is cross-sectional area times speed. So at the point I, or 1, we're going to have a rate of flow that will be equal or identical to the rate of flow at point F. Now I could use 1 and 2 for the 2 points. I've used initial and final. So this embodies both the definition of a volume rate of flow and the continuity principle, which says the rates of flow have to be the same at any 2 points. Let's try an example to show you how this works. So let's consider the flow of water through a garden hose. Okay, now the water that runs out here fills a 10-liter pail in 20 seconds. So this we recognize as a volume in liters, and this as a time. Now our principle, because we're calculating speeds in meters per second, we're going to need to convert this to cubic meters by canceling liters. Now there's a well-known equivalence which is given on your data page that a cubic meter of volume is 1,000 liters. So we see that this 10 liters of volume is 0.01 cubic meters. Time doesn't need to be converted. So when we set up the continuity statement, we know the volume rate of flow, which is the ratio of volume to the time, must be the same in the hose, that's the first location, as at the exit nozzle. Those are the same. So we know the volume and time, that's good. Now A stands for cross-sectional area. I'll put that in here, cross-section. And that is a circle. And the radius is given, so we can find the area of the circle as pi r squared. We just need to express the radius in meters. So we've got the volume, 0.01 over 20 seconds. and that's in units of cubic meters per second. Now the area is going to be pi r squared. Now at the hose it's 1 centimeter, or 0.01 meters. So that's pi r squared. We see the speed in the hose is the remaining unknown there. And this equation we can now use to solve for that. So we do 0.01 divided by 20 divided by pi divided by 0.01 squared, and then we'll get the speed of water as it flows through the hose. Now we have to have exactly the same. So the area of the nozzle is a lot smaller. It's 0.2 centimeters, or 0.02 meters. We still have to square that to find the area. And then this will be the speed in the nozzle, or the speed of the flow as it leaves the nozzle. So this continuity principle enables us to find these two speeds. Now I'll just calculate these offline and then put the results down for you. Okay, so if we solve for those two flow speeds, these are the results we get. So this, to solve for the nozzle speed, I hope it's clear, you take 0.01 and divide by 20, then you kind of ignore this, and you're solving for this unknown. So you divide by pi, you divide by 0.02 squared, and then that gives you the speed as it emerges from the nozzle. So at this point, just a really practical question, looking at the results of this, we can ask, so what happens if at a flow there's a constriction of some kind? Well, from the continuity principle, we know that once this flow is established, that we have to have the same flow rate at both these points, out here in the main channel and then here in the constriction. Well, clearly the cross-sectional area got smaller here. So in order to maintain constant flow rate, it must be that the speed here is going to get much larger. So if this was, say, a graphic showing the speed here in the main channel, the speed here in the constriction is going to get a lot greater. And in the previous example, we saw that at the nozzle, again, the speed greatly increased. So that's our first principle of fluid dynamics, the principle of continuity. Volume rate of flow is the same at any 2 points along the streamline, and volume rate of flow can be found as the ratio of volume to time, or cross-sectional area times flow speed. Our second principle of fluid dynamics we'll actually do a derivation of in class. But let me just present the result here and do a straightforward example. The second principle of fluid dynamics is Bernoulli's law. Now, actually, just let me back up, to this slide here. Because you may wonder, say in the example that we just did, why is it that the speed increases? So there's been a change in speed there. Doesn't that take a force? Hasn't there been some sort of change in energy here? What's causing this? Well, it turns out that there's actually a pressure loss. So if you were to measure the pressure here and then the pressure in the constriction, they're different. So Bernoulli's law governs this. And so what it tells us is, now to flip back ahead to the conclusion, there's a few pages of proof there that we'll do in class. It tells us that the quantity half rho v squared plus rho gh plus pressure is a constant. Now v is clearly the speed of the flow, and h is the height of the point in consideration. Rho is the density of the flowing fluid. And then P is pressure. Now in the statement we have rho and P, so you have to take some care to make your rho look different from your P. So ultimately what this is telling us is that you can have any two of these, but you can't have all three. So if one of them goes up, then one of the other two, or both of the other two, needs to go down. So in classical mechanics, there's a trade-off between speed and height. Say in a roller coaster, as you lose height, you gain speed. With fluid theory, it's actually or with fluid dynamics, let me say, it's a three-way trade-off between height, speed, and pressure. So this is the second principle of fluid dynamics, Bernoulli's law. Let's just do a simple example here to show you how it works. So here we're looking at the flow of water, and we're looking in side view, and we're pumping the water uphill, so there's a gain of 4 meters of height here. So we consider this point down here, and we know the speed is 2.5. Let's call this level down here a height of 0. And then we're given the gauge pressure, that's the pressure that would be read off a gauge. Remember, the actual pressure P is going to be the gauge pressure plus atmospheric. Now, in PSI units, atmospheric pressure, you'll recall, was 14.7 PSI. So this is 39.7 PSI, and we need to convert that to pascals for doing our calculations in SI units. Pascals is consistent with, meter per second units and things like that. So just let me pause you, and then I'll do that unit conversion. Okay, so that works out to 273 and 646 pascals. Okay, so that was just a unit conversion. All right, so now you'll see at the initial point here, we know the height, we know the speed, we know the pressure, and we know it's water, and the density of fresh water, something we should know. In any case, it's available on our data sheet. It's 1,000 kilograms per every cubic meter of water. Okay, so we have a complete data set for the initial point. Let's consider the final state up here. Well, clearly we're given the speed is 2, and we know the height of the final state is 4, so there's one unknown in this equation, and that's the pressure. So if we set up Bernoulli's theorem tells us 1/2 rho v squared plus rho gh plus pressure at the initial or start point will equal the quantity 1/2 rho v squared plus rho gh plus pressure up at the final point. So we substitute our known values then. Density of water is 1,000. Flow speed at the bottom was 2.5. Earth's gravity field's 9.8. The height was 0, so that whole term just disappears at the bottom. Then on this side, the speed was 2. And then we've got 1,000 times 9.8 times the height of 4 plus the unknown pressure. And so this is an equation that we can now solve to find that unknown pressure. So 0.5 times 1,000 times 2.5 squared plus the 273, 646. Then we subtract 0.5 times 1,000 times 2 squared, and then we subtract 1,000 times 9.8 times 4, and we get the final pressure of 235,571. And that will be in Pascal units. So that's how we use Bernoulli's theorem. And we'll be testing these two principles of fluid dynamics in the lab. First of all, the continuity principle, and second of all, the Bernoulli theorem. We will, in class, go through the derivation of the Bernoulli theorem and also do one more example, just to make sure you've got the idea straight.